Many researchers feel they are a strong candidate for dark matter, but there would need to be plenty of them to satisfy that theory. Just as the trail for such diminutive black holes appeared to have gone cold, an international team of scientists has found clues in quantum physics that could reopen the case. One reason the hunt for these so-called primordial black holes is so pressing is that they've been suggested as possible candidates for dark matter. Hey guys, welcome to Spaceverse. Tie your seatbelts as we dive into, if the Big Bang created miniature black holes, where are they? Also don't forget to like this video, and subscribe for latest space news. Dark matter comprises 85% of the mass in the universe, but doesn't interact with light like everyday matter does. That's the matter made up of atoms that comprise stars, planets, moons, and our bodies. Dark matter does interact with gravity, however, and this influence can affect ordinary matter and light. Perfect for cosmic detective work. If Big Bang-induced black holes are indeed out there, they would be absolutely tiny, some could even be as small as a dime, and therefore possess masses equal to those of asteroids or planets. Still, like their larger counterparts, stellar mass black holes, which can have masses tens to 100s times that of the Sun, and supermassive black holes, which can have masses millions or even billions times that of the Sun, tiny black holes from the dawn of time would be bounded by event horizon. The event horizon prevents black holes from emitting or reflecting light, making tiny primordial black holes a solid candidate for dark matter. They may be small enough to go unnoticed, but strong enough to impact space. Back to the Big Bang, to hunt for primordial black holes. The most favored models of cosmology suggest the universe began around 13.8 billion years ago, during an initial period of rapid inflation, the Big Bang. After the first particles had emerged in the universe during this initial expansion, space eventually became cool enough to allow electrons and protons to bond and form the first atoms. That's when the element hydrogen was born. Additionally, before that cooling happened, light could not travel through the cosmos. That's because electrons endlessly scatter photons, which are particles of light. Thus, during these literal dark ages, the universe was essentially opaque. Meanwhile, the atoms of hydrogen created went on to form the first stars, the first galaxies, and the first galaxy clusters. And, sure enough, some galaxies appeared to have more mass than their visible constituents can account for, with this excess attributed to none other than dark matter. Some scientists think conditions in the hot and dense early universe were such that smaller patches of matter could collapse under their own gravity to birth these minuscule black holes, with event horizons no wider than a dime, or perhaps even smaller than a proton, depending on their mass. The team behind this research has previously looked at models of primordial black holes in the early universe, but these models have failed. At the beginning, the universe was incredibly small, much smaller than the size of a single atom. Cosmic inflation rapidly expanded that by 25 orders of magnitude, director of Kavli IPMU and Resu Junichi Yokoyama said in the statement. At that time, waves traveling through this tiny space could have had relatively large amplitudes, but very short wavelengths. The team found that these tiny but strong waves can undergo amplification to become much larger and longer waves that astronomers see in the present-day cosmic microwave background or CMB. The team thinks this amplification is the result of coherence between the early short waves. If the team's theory that early, small-scale fluctuations in the universe can grow and influence large-scale fluctuations in the CMB is correct, this will impact how structures grew in the cosmos. Measuring fluctuations of the CMB could help constrain the size of the original fluctuations in the early universe. That, in turn, places constraints on phenomena that rely on shorter fluctuations, such as primordial black holes. Primordial black holes are firmly hypothetical at the moment. That's because the light-trapping nature of stellar mass black holes makes even these vastly larger objects tricky to see, so just imagine how hard it'd be to spot a black hole with an event horizon the size of a dime. The key to detecting primordial black holes may lie not in traditional astronomy, but rather with the measurement of tiny ripples in spacetime called gravitational waves. While current gravitational wave detectors aren't sensitive enough to detect ripples in spacetime from clashing primordial black holes, future projects, such as the Laser Interferometer Space Antenna, LISA, which will take gravitational wave detection to space. This could help confirm or reject the team's theory, bringing scientists closer to confirming whether primordial black holes could account for dark matter. That's all for today's video. If you are interested in space, universe, black holes, and stars, don't forget to subscribe to our channel for heated topics. Thanks for watching. See you in the next video.